Previously, we had looked at the conservation of angular momentum, where the sum of the angular momentas initially equals the sum of the angular momentas finally, or the total angular momentum before equals the total angular momentum after. And we didn't exactly give reasons why that's true, we just observed that it was true. So I want to spend just a little bit of time making sense of why angular momentum is conserved. Because what we did before is we just built on our intuition that if this is rotating counterclockwise and I grab and stop it, I started rotating counterclockwise as well. But we want to see why that's true. So to see why it's true, we have to look at the different pivot points. This is the pivot point of the wheel, and this is the pivot point of me. I'm sitting on this bicycle wheel a chair that will spin around quite easily. So if the angular momentum, if this wheel is spinning like this, to stop it, I have to grab and pull backwards with my hand. I got to put a force on the wheel in that direction. But if that's the only force on the wheel, the whole wheel would accelerate in that direction, right into my face. So my left hand here has to push equally away from my face so that it's not accelerating in the X direction here. Well, now let's look at the torques that those provide. This force is acting at this distance to the pivot point, so there is a clockwise torque put on the wheel, which is opposite from the wheel's angular momentum. This force was right in line with the pivot point, so that force didn't provide any torque. There was a net torque on the wheel opposite the angular momentum, and that's why the angular momentum slowed down and eventually stopped. But now let's look at Newton's third law. Remember that if my hand puts a force on the wheel to the left, the wheel is going to put a force on my hand equally and back to the right. It's just an action-reaction. Well, that force here acts in this line of action, which is this distance to my pivot point. This is a force on me, and that force is acting at a distance from my pivot point, which puts a counterclockwise torque on me. Notice that it's the same direction that the wheel was initially turning, and that's why I will start rotating that same direction. This force from the reaction of my hand pushing the wheel to the right, the wheel pushes my hand to the left, that force just goes right through the pivot point, so that one didn't produce any torque. This one right here was the net torque on me. Okay, well, let's see if instead of grabbing the wheel here and pulling backwards, what if I had reached around here? It would have been a little awkward, but the wheel was spinning this direction, so to stop the wheel, my hand would have to push up on the wheel there. Well, if that was the only force acting on the wheel, then it would accelerate that way, so my left hand is pushing nearly equally down like this. Now let's look at the torques. This force is acting at this distance to the wheel's pivot point, and that is going to produce a clockwise torque opposite the wheel's angular momentum. This force went right through the pivot point, so no torque. There was a net torque on the wheel opposite the angular momentum, so it slowed down. Okay, but now again, let's look at action-reaction. My hand pushed the wheel that way, so the wheel is going to push my hand this way. That force is on my hand is acting at this distance to my pivot point. That is going to produce a clockwise torque on me. And you might pause there for a second and say, wait a second, I thought I was going to rotate counterclockwise, but there's a clockwise torque on me. Well, there's more to it. Remember this one. My hand pushed the wheel down, so the wheel is going to push my hand up. That force on me is acting at this distance from my pivot point. This force was nearly the same as this force, but it wasn't the same distance. This force acted at a much greater distance, so the torque in this direction was a lot greater than the torque in that direction. There is a net torque in the counterclockwise direction, so I begin to rotate counterclockwise. Action-reaction is just what explains conservation of angular momentum. But we have to do action-reaction with torques. All right, now let's look at angular momentum as a vector quantity. If angular momentum has magnitude, like bigness, if it's a little angular momentum or a lot of angular momentum, it has magnitude. And if it has direction, well, then that's the second part to being a vector. So this wheel here is rotating clockwise with a little angular momentum. This one is rotating clockwise with more angular momentum. So these two have the same direction, but different magnitudes. These two are rotating in opposite directions, but with the same magnitude. All right, so if angular momentum has magnitude and direction, we should be able to represent it with a vector quantity, which is a straight arrow. So this arrow was longer, saying it has more magnitude than this one. These had the same length, so same magnitude, but pointing in opposite directions. Okay, so we should be able to do that, but I haven't told you how to do that yet. The challenge here is to be able to take this curved arrow and turn it into a straight arrow that we typically do vectors with. We're going to change these equations to have vectors over the top of it. And that's going to open up a whole new world of problems that we can now understand. So if this wheel is spinning clockwise like this, previously we would have drawn this curved arrow, an arc, representing its angular momentum. But how do I turn that into a straight line? Well, maybe we should just continue that arrow as a tangential angular momentum. That's one way possibly. But we forget this curve here is representing something that's going around and around and around. So if it is going around and around and around, the direction of my straight vector is constantly changing. What we need to do is find a consistent way that will take that and put it into a straight direction that is not changing, because the direction of this spin is just doing the same thing. Nothing's changing. So the way we're going to do that is, instead of drawing a vector in the plane of its rotation, we're going to draw a vector perpendicular to the plane of rotation. So that as this spins round and round and round, the vector representing its momentum is always in the same direction. So here we have something spinning around with angular momentum like this, and we have to turn it into a straight line. We're going to use a right-hand rule to do that. This is the first of many right-hand rules, but it is just a convention, which means there's lots of different ways we could have done this, but because a lot of people have right hands, and we can use our right hand to find a consistent way of doing this, that's what we're going to do. So here's the rule. If something is spinning around like this, and we look at the axis for which it is spinning, we take our right hand and grab that axis, curling our forefingers in the same direction of the spin. Okay, so my forefingers are curling around in that same direction. Our thumb is sticking up like this, and our thumb is going to be pointing to the direction of its angular momentum, which is just a convention. We could have done it different ways, but we just all are going to agree to do it this way, and it seems like a good way to do it. If we do the same thing over here, and we had, instead of grabbing from the right-hand side, we had grabbed from the left-hand side with our right hand, it'd be the same thing. Our forefingers are curling around like this, and our thumb points to the direction of the angular momentum. If the object had been spinning the opposite direction, if it had been spinning around like this, we just still grab the axis of the rotation with our four fingers curling around this way, and now the angular momentum is pointing in the same direction as our thumb. It's pointing down. Okay, and this will allow us to do it in 3 dimensions. Any way we want to do it, we can figure it out with our right hand. If it's spinning around like this, the angular momentum is coming out. So angular momentum was rotational inertia times angular velocity. And a change in the angular momentum was torque times an interval of time. So what you need to do here, and I'm going to hit pause I'm going to have you hit pause in a moment, is limber up your elbow and take your right hand and get your right hand in each of these 6 positions. Hit pause and do that. I hope you hit pause and did that. I hope you did not deprive yourself of making synaptic connections in your brain, but you really do need the practice of being able to get your hand in these orientations. But that would be a vector representing angular momentum. Angular velocity is also a vector quantity, so we should be able to do the same thing with this. Torque is also is a vector quantity, so we should be able to do the same thing with torque. All right. What that does now is it will allow us to do problems that we've been familiar with, like adding different vector quantities. If this is an object spinning around like this, we can show its vector angular momentum by an arrow pointing off to the left. That's our right hand curling around the axis in the direction of the spin. Okay. Now this ball appears to have the same velocity, angular velocity, but it's smaller, so it would have less angular momentum. And again, our right hand is going to be pointing, our thumb is going to be pointing down. This one would have angular momentum off in that direction. And if we put all those inside a box and we want to find the total angular momentum, the sum of all those, that would be very difficult to do if you're drawing arcs and circles. But it's very easy to do if you're drawing straight line vectors, because we just take head to tail. The head of one, put it to the tail of the other, and the head of this one to the tail of that one. The resultant goes from the tail to the head, so the total angular momentum would be with an object something like that. Opens up a whole new world for us. Okay, now let's see how torque will change angular momentum. And remember, change in angular momentum is just going to be what it finally was minus what it initially was. So here we see that the initial angular momentum is parallel, but in the opposite direction to the torque. And we might guess that that's going to cause us to slow down. It's going to cause it to change its magnitude. Because if we put a torque opposite of the way it's spinning, we're going to slow it down. Okay, but what happens here is that, and here's the big idea, don't miss this. The change in angular momentum is going to be in the same direction as the torque. So if the torque was this direction, the change is this direction. It went from this to this. It changed down there. And that's what we did here. If we had the angular momentum in one direction and put a torque in the opposite direction, it decreased its magnitude. Here we have angular momentum in that direction, and we're going to put a torque at right angles to that. So if this is the initial and we put a torque at right angles to it, the final momentum is going to be like this, because the change in momentum went from here to there. Notice the change is in the same direction as the torque. It's like if I pull down or push down on my left hand here and pull up on my right hand, the torque, like this, was at right angles to its angular momentum. Okay? Or we can do it a little bit of each, where the angular momentum had a component, the torque had a component that was parallel and a component that was perpendicular. So if we put a torque on it in this direction, the angular momentum is going to change from that to something like this, where this is going to make it increase its angular momentum, the magnitude. This is going to change its direction. Okay, so the change was off in this direction, which again was in the same direction as the torque. Okay, so how do you do that? Well, this is a little exercise ball, which is a gyroscope that I use to strengthen my forearm for rock climbing. And you get this spinning around a little bit, and then you move your wrist in the shape of a cone, kind of like this. So as I put a torque on it, there is a component of that torque that will increase its magnitude, and there's a component of the torque that's going to change its direction. All right, I'm going to diverge here just for a little bit, but this is an equal sign. Yes, we got that one. And remember that if it had three little lines, it's better than equals. It is the definition. And in physics, we have lots of definitions. Okay, they might be big definitions, they might be small definitions, but they're still definitions, and you need to know the definitions. The trouble comes when there's lots of definitions, and you have to try to make sense of all those things. And it's easy to focus in on one little definition and forget how it relates to other definitions. For example, if we do that, we might miss out on the actual physics. You might recognize, or you may not, that this says physics. Okay? And if you're staring at just the little definitions, you will miss that. For example, this picture here had lots of stuff going on in there. And if you stare at one little thing or the individual pieces, you miss out on the big picture. The big picture here is that angular momentum was conserved because action-reaction with torques. Okay, so let's see if we can see that a little bit better. If we stand back a little bit, maybe we can see that that says physics. You see it? There it is. All right, I told you I was going to diverge there a little bit, but that's just a sign I have on my lecture table here. Okay, but we do need to make sure that we are standing back and seeing the big picture. This is a drill that I have this device on that is going to power this up real fast. A little dangerous here. I wouldn't recommend doing this yourself, but what I want to do is see how torque changes angular momentum of this wheel. I'm letting go with that hand and just balancing the end of it with my hand here. If I switch and hold it on the other side, I'm just balancing there. The whole thing starts to rotate this direction. And I'm coming back to just balancing on there, and it starts to rotate the other direction. That would be really hard to understand if we didn't have vectors. So gravity is pulling down on the center of gravity of that wheel. That force is acting at this distance to my hand, is where the pivot point is. So that puts a torque on the whole wheel in this direction. Our right hand says that's going to be a torque pointing in to the board. All right, this wheel was spinning around like this. The top of it was coming toward me. The bottom of it was going away from me. Our right hand says it has angular momentum off to the right. Okay, so the momentum was off to the right. The torque was into the board. And the change in angular momentum is going to be in the same direction as the torque. This momentum is going to turn toward that way. It's going to turn around like that. And that's why the whole thing was rotating like that. That would have been very, very difficult to do by just looking at these arcs without looking at straight line vectors. Well, let's apply this to riding a bicycle. If I'm riding a bike without hands and I want to turn this way, coming around like that, the wheel is going around and around like this. The top is coming toward, the bottom's going away. Our right hand rule says the angular momentum is going to be to our right. If I lean over like this, now my weight is on the left-hand side. I'm putting a torque on the whole bike like this, counterclockwise. Our right hand says the torque is going to be coming straight at us. So what does that bicycle wheel do when it has angular momentum this way and we put a torque on it this way? Well, the angular momentum is going to turn toward the direction of the torque. The wheel is going to turn around like that, and that's what makes you turn. So I have a serious question here. My question is, how many of you know how to ride a bike? I'm serious there. My question is not, can you ride a bike? My question is, do you know how you ride a bike? Well, let's see if you are correct in thinking you do. If you're going to turn this bike to the left, Do you take your right hand and push it forward there and take your left hand and pull it back a little bit there? Do you put a torque on the handlebars like this to make the bike turn to the left? You don't. That's not what you do. And you know that you do without maybe knowing that you know you do. Maybe I should explain. Our right hand says that if we put a torque on it like this, there's going to be a torque in the up direction. And if the wheel is spinning around like this, our other right hand rule says it's going to have angular momentum off in that direction. So if it has angular momentum to the left and I put a torque on it up, the angular momentum is going to change that way, which means the whole bike is going to rotate to get more angular momentum in that direction. Now if you're trying to turn left and the whole bike leans to the right, you're going down. Okay? So you know that's not what you need to do. What you do is you put a different torque on it. You put a torque on it in the opposite direction. Well, yes, you do. Here's what happens. You pull your hand back this way, you push your hand forward that way. There is a torque on it like this, which is now in the down direction. The momentum was to the left. The torque on it was down. The angular momentum is going to turn toward down, which means the whole bike is going to lay over to the side like that. Remember, we're trying to turn left. At that point, you don't put any force on your hands. You just hold on, because now your weight is off to the left. Your weight puts a torque on the bike like that. Well, if there's momentum off in this direction and there's a torque off in it in this direction, the momentum is going to change toward this direction and the bike turns left. So you turn right to go left, which means you got to turn right just a little bit to get your weight over there on the left. Then now you go left. And you might have discovered that if you were riding your bike next to a curb or on the edge of the sidewalk next to the grass, and if you're right on that edge and you have to turn left to get away from it, you find yourself kind of stuck. You think, I can't get over. And that's because you have to go right just a little before you can go left. This is an old exercise bike wheel that I cut up and I mounted inside of a suitcase. And you can use a crank and get this thing spinning really, really fast. But with the suitcase closed, you can't see inside. So I've just finished cranking this thing. I'm not telling you which way I'm cranking it. You get to figure that out. But the wheel inside there is spinning really fast, and then I'm going to take that whole suitcase and put it on this turntable at a little bit of an angle, and notice what gravity does to that. It's falling over in its own special way. And then if I come around and I change the direction of its tilt, it starts rotating in the opposite direction. Okay? So I'm going to ask you to think about that and figure out which direction the wheel is spinning inside that suitcase. You have enough tools to do it. Hit pause and try to figure it out. Now that you're back, I hope you hit pause. Let's see what's going on. Is the angular momentum going this direction or is it going this direction? We do know that the whole thing was rotating around like this. So this tip would have been rotating this way, or this tip would have been rotating that way. We don't know which of those it is just yet. That suitcase is touching down here, and a lot of its weight is off to that side, so gravity is putting a torque on it like that. Our right-hand rule says the torque is going to be into the board. So which of these two was it? The angular momentum will change in the same direction as the torque. Okay, so this angular momentum is going to go more toward that direction. If it had been this one, it would have gone more toward the opposite direction. So it must have been this one. And our right-hand rule says the angular momentum must have been spinning around this direction inside that suitcase. Here's a little conundrum. It's called a rattleback. But if I spin that thing one direction, it does fine. It just spins just great. But if I spin it the other direction, It doesn't like that, and it starts spinning the original direction. What? Its angular momentum just changed. And if I just tap it there, it starts going that same direction. I have to be honest with you, I have no idea how to explain this. No idea. I'm really not kidding. Okay, but at least I know where to start. If it changed its angular momentum, there must have been a torque on it. This is looking at that same object from the view right along its long axis. So that right there is the top of it. And it's a little asymmetrical here. A little material is missing there. So as it spins around, it's going to be touching the glass right there. There's more material off to the right, so there's a torque on it right there. Or there's a force at that distance. There's a torque on it. Okay, so without fully explaining it, at least I know where to start. Now, it wouldn't do justice to angular momentum vectors if I didn't introduce I, J, K notation. And I'm not teaching this here. I just want to say, hey, this is the next step. This is where you go to from here. But we have the x-axis, the y-axis, and the z-axis, and we would like to be able to do math in 3 dimensions. And if we can do that, we can do math in 4 dimensions or 5 dimensions or any number of dimensions. If this is a vector 1 unit long in the x direction, and I put 4 of those all in a row, well, that's just going to be 4 times that vector, 4i. If this is a vector in the positive z direction, this would be negative z, and another negative z makes, k, negative 2k, twice as long as just one of them. And then if we had 3 in the y direction, this would be 3j. This is the x-axis, the y-axis, and the z-axis, but we have vectors I, j, and k. What that allows us to do is we can describe a vector here in 3 dimensions. So we could have the components of this vector be 4i, 3j, and negative 2k. And we can write it as just like taking this plus that. Because if I take 4i and I add this head to tail, add this to that, and then I add this head to tail, the resultant is going to go like that. Okay? And then if I defined another vector, I'm not drawing that one, but we had this one, and that one, we can do all sorts of math on that. We can add those 2 vectors. We can subtract those 2 vectors. But I want to introduce a new concept. We can dot those 2 vectors, or we can cross those 2 vectors. I'm not going into any detail on those right now. I'm just saying this is what's next. So enjoy. I hope you learned a little bit. That's angular momentum as a vector quantity.